Welcome, lazy chemists, to today's lecture on Hess's Law, or how to cheat thermodynamically. Okay, so what we've been doing so far with thermochemistry is we have been doing reactions, and then we've been recording how much energy is released by that reaction into the environment. What we're now going to do today is we're going to go ahead and figure out a way to kind of cheat that system now. So, as you can imagine, if you're doing and trying to figure out stoichiometric processes or trying to figure out thermodynamic processes, doing an actual experiment for each and every one of those and then calculating how much heat is lost is going to be something that would end up taking quite a lot of time. So trying to do that constantly would end up, just being too much work in general. So what we have here is a law that's called Hess's Law that will allow us to kind of cheat that system a little bit. And it'll make it so that instead of doing an entire experiment for a reaction to figure out how much enthalpy is gained or lost, we could go ahead and do a little bit of math to figure it out without having to go through that entire process. Okay? And the definition, or the formal definition for Hess's Law, basically states that the total enthalpy change of a reaction is independent of the route by which the chemical reaction takes place. Right? So this is like the formal definition. But this is kind of like a useless definition because it doesn't really help us out. It's all in chemical jargon. Instead, we're going to go ahead and re-explain it and say it doesn't matter how you made the reaction happen. The energy change between the initial and the final state is all that matters. Therefore, we are going to want to make sure that we use the easiest to calculate path to determine the amount of enthalpy change. So, this is a diagram that we're going to use to go ahead and help explain it here. And essentially, what will happen is that we're going to have an enthalpy change. We're going to have our products going from A to B. And delta H1 is going to be our primary concern for solving this problem. Okay, but we're going to imagine that we cannot directly measure delta H1. We're going to imagine instead that we have to go through some form of intermediates, okay? And what Hess's law states is that if we add the delta H here, or the change in enthalpy here going from 2C, and add that to the delta H of going to B, then we're going to get the same answer as we have for delta H1 right here. So that means that if we go this route is going to give us the same answer as going this straight route right here of going straight through delta H1. Also, if we go this route, this longer route right here, that's also going to be a more direct route. All right. Now, there are going to be some times where you are given a reaction pathway, okay? And, what that actually means is that you'll be like, oh, okay, it says that from A to D is this much, and from D to E is this much, and from E to B is this much. And that's great. That's one method. The most common method and the most practical method that there is, though, is going ahead and going to the enthalpy of formation. And that's usually what I see being done because the enthalpy of formation, almost all of those compounds that we have the enthalpy of formation figured out, and we would be able to go ahead and do the math for those really, really quickly because it's already figured out in a table. And that's going to be the first method that I show you because I think that one's the one that we should explain first. Okay. So just a reminder that the overall enthalpy of a reaction is going to be the enthalpy total is going to equal the products minus the reactants. And we're going to use, some basic functions of this to go ahead and solve. Okay, so we're going to go ahead and use the example of burning ethanol. Okay, so ethanol is a compound and it's C2H5OH. It burns in the presence of oxygen gas to form CO2 plus H2O. And here we're going to be given the enthalpy of formation. We have the enthalpy of formation for C2H5OH. We have the enthalpy of formation of oxygen, okay? And remember, anything that's an element that's in its original state, we have the standard enthalpy of formation of that as 0, okay? We have the enthalpy of formation of CO2, and we have the enthalpy formation of H2O, okay? So essentially, we have C2H5OH and oxygen. So we have our starting materials here. We have their formations. And we have CO2 and H2O. And this is our final products right here. All right? But we're not given anything else. We're not given an alternate pathway. We're not given what the actual delta H is here. And we need to figure this out. Okay? So our best way, given that we're given the enthalpy of formation, is we're going to say, okay, let's go ahead and figure this out by going to our original elements here, okay? And then let's go from our original elements to our products, which is going to be CO2 and H2O, okay? So what I've done here is I've went ahead and I've made the actual formula. So this is our formula for C2H5OH and oxygen coming together to make CO2 and water, okay? And that's this reaction right here. I also made the initial reactions to go ahead and get us to our initial products, okay? So this reaction is how we make, this is the reaction that we need in order to make ethanol, okay? So carbon plus oxygen plus hydrogen is going to end up giving us ethanol. And we have our standard formation of ethanol right here. This is the number 4. This is the standard formation of ethanol. Okay, we also have our graphite and oxygen coming together to make CO2, and that's part of H3, okay? This is going from our elemental form to CO2. And I also have the equation for solving for making water, though I don't have it balanced correctly. And water is also part of this because it's going from its elemental state to a final state. Notice that here, for all of our products, for H2 and H3, we are using elementals to solve it here. Okay. These right here are going to be our instructions for how we do it. The first thing that we're going to do is we're going to go ahead and balance our reactions. The reason that we need to balance them is because when we notice here, all of these enthalpies end up being in kilojoules per mole, which means that we're going to want to make sure that we are using the right number of moles for each one. Okay. Then we're going to go ahead and multiply the pathways by the number of moles in the original equation. We will flip the signs to ensure that the reaction is going the right way, and then we're going to add our enthalpies together. Okay, now let me show you what I mean by that here. Here, this is carbon going to graphite and O2, but notice that we're not going from C to A. We're not going from this stuff to A. We're going from C2H5OH to our elements. So that means that this one, H2, is going to have to be flipped based off of what we see here. Okay. Now, our first step to balance it is to, well, just to balance it. Okay. In this particular case, we're going to go ahead and say, all right, we have C2H5OH, and we balance it out to make this right here. Now, this means that when we go through and do our, multiplication of this, that we're going to need to make sure that we have the right amount of products for this, okay? So that means that when we go through and we, figure out how much energy we make, we're going to need to make sure that we make 2 moles of CO2 and we make 3 moles of H2O. Okay, we balance this one out right here. This one's already balanced. This one is not balanced, but it still makes 1 mole of H2O, so we're just going to keep that in mind as we go through here. Then we're going to multiply the pathways. Notice that this is the pathway to make CO2, so we're going to multiply it by 2. This is the pathway to make water. We're going to multiply it by 3 because we have this 3 here for water. We're going to, and right here I've already multiplied it by 2 and multiplied it by 3. We're going to flip if it's a reverse process. So here we start with C2H5OH. And we're going to graphite and everything, so we're going to go ahead and flip that process. And then we're going to go ahead and add up all the enthalpies of that reaction. So you just have to go ahead and open and add up all of those. Okay, I'm going to give you a second to go ahead and solve that. All right, and once you have solved that, you should end up getting an answer that's 1,243.02. You're going to go ahead and double check that your answer makes sense. In this case, I have a negative answer, which says that it's an exothermic reaction. I'm going to make sure that makes sense in my head. This is ethanol burning, which releases heat. So that means that it is a... that reaction does make sense, and that's going to be our answer. So it's going to be 1,243 kilojoules per mole. And that's how we solve for H1. And that's, especially if you are given like your standard enthalpies of formation. Now, this is a second example. So I use this example right here because I think that this example is a little bit more useful. But the second example that is sometimes used is that they'll go ahead and put it in terms of a reaction progress. But realistically, it's just the same thing. Usually what's going to happen is that you're going to have your reaction step, your initial materials right here, your reactants. You'll sometimes have your intermediary step right here, and then you'll have your products right here. With problems like these, what's often going to happen is that they will give you a reaction step. So this will be reaction step 1. This will be reaction step 2. And if you get something that's like that, that means essentially that you just have to add those steps together. Okay, so to go from N2 and O2 to NO, that takes and absorbs about 90 kilojoules. To go from NO to NO2, that's going to release 56 kilojoules, okay? Which will end up giving you a total of 34 kilojoules per mole, okay? So your delta H total is 34 kilojoules per mole. We may have taken a side path to get there, but that's the point of this particular, reaction process. That it doesn't matter which method we use to get there, as long as we have a method that we can quantify how we get there. All right. So this is going to be the end for this lecture on Hess's Law. I hope that you guys, enjoy it and find a nice way to kind of cheat while doing these, calculations of enthalpy right here.